Well, this is the final module of the course, and we're going to be taking a look back at what we've learned, but mostly taking a look forward at the nature of what's going on to the climate of the planet, um, the effects of climate change. And so this module takes a look starting off at effects of climate change um, beyond just it's warmer. There's a reason that what we used to commonly refer to as global warming, we now refer to as climate change, and that is because there are many, many effects of the increase in energy in the atmosphere beyond just a warmer surface temperature. So the energy increase is due to increased greenhouse gases, which trap some of the energy that's trying to radiate away from the surface of the Earth into space. And that extra energy in the lower part of the atmosphere first makes things warmer. But then, of course, if it's warmer, that does things like melt ice and change weather patterns. If you're melting ice, then you're changing uh, the salinity of some parts of the oceans. Um, if you are putting more CO2 into the atmosphere, then you're absorbing more CO2 into the oceans, which makes the oceans basically more carbonated. And that's carbonic acid. That's like uh, turning the oceans more into a soda, like Coke. And so there are a number of different aspects of climate change, and many of those are listed here. But basically, these changes due to increased energy in the atmosphere, increased melting of ice, changes normal weather circulation patterns, changes oceanic circulation patterns, and all of these things then have consequences for the biosphere, plant life, and animal life as well. Let's talk a little bit about the temperature change. So, of course, there's a difference between climate and weather. One analogy that's been made is that climate is your personality and weather is your mood. So weather is more volatile. That's captured here in this slide, which shows a distribution of temperatures. Of course, on any given day, you can say, what's the temperature like in New York City in the middle of March? Well, you can look up an average temperature for that time. But of course, some years it'll be warmer than that, and some years it'll be colder than that. And if we take a look over the course of a very large number of years, we would get a distribution, a Gaussian or bell-shaped curve like you see here. And with climate change, increased energy in the atmosphere, these temperatures are shifting to warmer temperatures. So the blue curve shows a distribution that has an average temperature of 15 Celsius. And if there's a climate change that leads to a 2-degree warming, then what that does is that means the average temperature shifts to 17 degrees Celsius, but there's still a broad distribution here. So that's illustrated by the red curve. Now, the inset in the circle shows the high temperature tail of these distributions. And while you may say, oh, well, most of the time the temperature is just a couple degrees warmer, what's the big deal? One aspect of the big deal of that is that it greatly increases the frequency of high temperature events. So if we look in this little circle inset and, for example, take a look at where it says 30 degrees C, for the blue curve is barely above zero at 30 degrees C. The red curve looks like it's about, I'll say 1, 2, 3, maybe 4 to 5 times higher than the blue curve at 30 degrees C. And at 28 degrees C, it's also several times higher. What that means is you're 5 times as likely to have a very, very hot day, even though the average temperature has only increased by a couple of degrees. In other words, if we look at the main plot where it says 17 degrees, the red curve is barely above the blue curve, meaning the probability of having the temperature be 17 degrees is only a few percent higher than it was before climate change. But at those higher temperatures, at the very high temperature events, which are ones that can cause lead to fires because they're drying things out, and it can lead to people dying from overheat if the cooling systems are not working. Those occurrences become much, much more prevalent. Sea level rise is something that gets a lot of attention as well. Of course, if we increase the temperature, then we're increasing the rate of melting of ice. And if you melt an iceberg that's floating in the ocean, that doesn't do anything to the sea level. You can do this experiment with yourself. Take a glass, fill it halfway with water, put some ice cubes in it that are floating, that are not resting on the bottom, and notice that, put a mark, and you can see as the ice melts, the water level doesn't rise because the water is already supporting that ice, so as it changes phase, it doesn't rise. But we have a lot of ice that's on land. So that's why this table specifies sea level rise from melting land ice. And the land ice is primarily in Greenland and Antarctica. About 85% of it's in Antarctica, where there's land ice that's about a mile deep, and then a significant amount in Greenland, and then mountain glaciers spread around the continents of the world. So in the 20th century, most of the sea level rise that has occurred so far is due to the melting of glaciers. Like if you go to Glacier National Park in the United States, you can see that those glaciers have retreated. If you look at glaciers in Europe and Asia, they have melted. That water runs downstream and into the oceans. That's accounted for about 8 centimeters of sea level rise in the 20th century. About another centimeter or so of sea level rise due to melting of ice on Greenland and Antarctica. So one question is, what happens if you melt all of it? If it gets warm enough, you just melt all of the land ice. How high does the sea level rise? And the answer is about 70 meters, or about 230, 240 feet, something like that. So if you add these numbers up, 62 meters from Antarctica, another 7.2, 7.5 meters from Greenland and mountain glaciers. So that's about 70 meters of sea level rise potential. So if you've seen the movie Waterworld with Kevin Costner, where Mount Everest becomes a little tiny island, we don't have enough water to raise the sea levels that high. But even a sea level rise of only a few feet can be quite devastating. Another consequence that was mentioned previously is increase in storm energy. 2020 has just tied the record for the most named Atlantic tropical storms and hurricanes. We've got Hurricane Eta right now in November of 2020, tying a record that was set in 2005. So here is a look back in time that tells us that this isn't just sort of fanciful or terrified thinking. We know from studies of cores, as well as just looking at rocks and fauna and fossils, that during the most recent ice age, the Canada was covered by about 2 miles of ice. And that ice melted at the end of the last ice age about 8,000 years ago. And when it did so, that led to a dramatic rise in sea levels. And we can see that. So, for example, England used to be part of Europe when at the end of the last ice age. That filled in the shallow part between what's now the United Kingdom and continental Europe, creating the English Channel. So if we go back 20,000 years, this green indicates the land extent of what is now Florida. And you can see that the eastern seaboard, this continental shelf that's now underwater, would have been a much larger coastline. You can see that some of the islands in the Bahamas would have been much, much larger low-lying areas. And if we take a look at what that sea level rise has looked like, or what the sea level has looked like over the course of time, you can see that in figure 2.2 on the right here, at 18,000 years ago, the sea level was 120 meters deeper than it currently is. And at the end of the Ice Age, it rose quite rapidly. So we've got historical, not even that old evidence for dramatic changes in the depths of the Earth's oceans. In the last 20,000 years, the sea level has increased by over 100 meters. And where we are now, the sea level is rising again, and the rate of increase of the sea level has sped up. Again, this is another look at the rate of sea level rise. So it's not looking at the sea level itself, it's looking at the rate of sea level rise in millimeters per year. Let's shift that figure a little bit. What this is showing on the left, these numbers, 10 millimeters per year means at that time the sea level was going up by 1 centimeter a year. 25 centimeters is an inch. So 10,000 years ago, the sea level was rising an inch a year, and that's quite dramatic. At the moment, it's rising at a much slower rate than that, but the rate is increasing. So what are the projections for what the sea level will look like in the future? It depends on these pathways, which depends on how much extra energy we're trapping in the atmosphere due to greenhouse gases. Remember, the business as usual number was 8.6 watts per square meter. The sort of ideal would be to bring that down to zero. But if we take a mid case of 4.5 watts per square meter, RCP 4.5 scenario, which is even now I would say probably a fairly optimistic forecast, then at the end of the current century, we're looking at a sea level rise of between maybe 70 and 120 centimeters or so, roughly a meter increase in sea level. So that's maybe doesn't sound too bad. Here are some other projections of what the sea level rises might be, depending on over the course of the next century, depending on different estimates. But you're looking at ballpark half a meter to a meter, depending on how optimistic or pessimistic you are about what those sea level projections will look like. So, what does that kind of sea level increase translate to? Well, if we look at the collapse of the West Antarctic ice sheet by itself, and that would be the result of a positive feedback effect where warming water causes the underside of that ice sheet to melt and it loses its support, and then all of that land ice very rapidly flows into the ocean before it even all melts. Then we're talking about a 3-meter rise in sea level, and you can see that that would wipe out all of South Florida and much of the rest of coastal Florida. If we melt all of the world's land ice, then you're taking out a good chunk of southeastern United States, fair amount of central northern California, and most of the eastern seaboard. That 70 meters, that could totally happen. So we could, these things, you can't just stop it. That heating, once it's going and the temperature rises there, the ice will melt. And as we've seen a few slides ago, there are historical examples of the sea level varying by hundreds of meters. And in fact, if we go further back in time to the age of the dinosaurs, there was a great inland sea over much of the central part of the United States when there was virtually no land ice and there were tropical temperatures in Canada. So sort of think of times of the dinosaurs, 6,500 million years ago. So it's totally possible all that ice would melt. It's probably not possible for all that ice to melt in your lifetime. In your lifetime, we're probably talking about 1 meter increase in sea level. So what can be done? What's happening? We're putting huge amounts of CO2 into the atmosphere. As we have said several times before, CO2 is a necessary byproduct of burning fossil fuels. If you're not producing CO2, then you're not actually burning the fossil fuels. So we're pumping a huge amount of fossil fuels carbon dioxide into the atmosphere. We're at about 10 or 11 gigatons per year at the current rate, and that has been increasing, and as a result, we see that the atmospheric concentration of CO2 is increasing as well. Historically, again, we've seen that the CO2 concentration has fluctuated, but if we go back 500,000 years, as shown in the figure in the lower right here, those fluctuations have been between about 180 and 280 parts per million. We're currently at well over 400. This chart says 401, but that's a few years old. We're at over 410 already. So it's increasing quite dramatically and making the last million years or so pale by comparison. So we're doing a very interesting large-scale experiment on the planet at the present time. Based on previous measurements of carbon dioxide historically going back millions of years and the temperature at that time, we can predict what sort of sea level rise we'll get. And we talked about this when we were talking about climate models. At the current time, we've seen about a 1.2 degree increase in temperature since 1850. And you can notice this is nonlinear. So the temperatures were not changing very much between 1850 and, say, 1920 or World War II. And then they've been increasing somewhat more rapidly over the course of the last 50 or 60 years. Remember that we have this complicated carbon feedback system. We can put CO2 in the atmosphere, maybe put a little bit of extra CO2 in the atmosphere, and then maybe all of that extra CO2 that's going into the atmosphere just gets absorbed into the oceans, and it doesn't actually result in more CO2 in the atmosphere and result in higher temperatures. It's affecting the oceans, it's doing some other things, but it's not necessarily heating up the planet. But the planet only has a limited ability to buffer or moderate those increases. And because our rate of putting CO2 in the atmosphere has been increasing, we're now at the point where we're dumping so much in, the planet is unable to compensate for that. So our net increase now, our input of, say, 11 gigatons of carbon per year, the planet is only able to absorb about half of that back. And so that's why we see this non-linear response where now the temperature is increasing much more rapidly. These plots are showing, based on these different scenarios, these different pathways, which again, the numbers represent the amount of watts per square meter of extra heating, and the high number, the 8.5 watts per square meter, is the business as usual scenario. What the predicted levels of CO2 emissions would be in gigatons per year, and again, we're currently at about 11 gigatons per year, what these would be at the end of the current century. So if we continue business as usual, by 2100, we'll be putting 3 times as much carbon into the atmosphere as we currently are. And if we've already sort of maxed out the oceans and the biosphere's ability to absorb that carbon, that means that the current net increase, which is about 5 gigatons per year, would go from 5 to, say, 25, 30 minus the 5 that the planet is absorbing back, which is a factor of 5 increase. So there's this nonlinearity to the response. We continue business as usual. That would lead to a CO2 concentration at the end of the century of about 1,000 parts per million, which is about 0.1% of the Earth's atmosphere would be CO2. It's currently about 0.04%, and a couple of hundred years ago it was about 0.03%. And then what the temperature rise would be as a result of that, the business as usual scenario, we're looking at maybe a 5 degree C temperature increase at the end of the century. We've already seen about a 1.2 degree C increase from the pre-industrial revolution baseline. And in the best case scenario, we're still looking at a temperature increase of about 2 degrees, so another degree or so warming of the planet. This plot shows the ocean temperature going back now tens of millions of years. And the if we go back 35 million years, when the CO2 level was 450 parts per million, there were no ice sheets. So, in other words, that mile thick deposit of ice on Antarctica only started to form when 35 million years ago, when the CO2 level dropped below 450 parts per million. If we go back a slide, 450 parts per million, well, already we're at 416. So we're very likely to far surpass that 450 parts per million of CO2 in our lifetimes in the next couple of decades. And then we will be in this zone that's indicated by the red curve here, where historically that was enough extra warming due to CO2 in the atmosphere to completely melt the Antarctic ice sheets. The northern hemisphere ice sheets um, went away even at a later time. And so it takes time for all that ice to melt, but the last time the atmospheric CO2 concentration was above 450 million, there was no land ice on Antarctica. Right now we're at 416 and rising. And then we've seen these sorts of plots before, showing that we're currently in this unusually long, steady, warm period. The green curve shows the forcings due to CO2. The red curve shows the temperature, and they line up very, very tightly. And the green curve is going up. That's going to pull that red curve up. So what will our carbon emissions look like going forward in the next 10, 20 years? That's something to watch. We're at 11 gigatons per year right now. And the best case scenario, we have to actually not only stop putting carbon into the atmosphere, but start pulling some out in order to get those rates down.